The agenda for the one-way ANOVA comparing group means in an unbalanced setting is following. We're going to set up the hypothesis test, and then we're going to look at the distribution of the test statistic under the null and the alternative. And calculating power in this setting is pretty straightforward. However, calculating sample size is not, we need to introduce a little more structure. It's not straightforward, and then all this will be illustrated within R. So here our data is follows, this is the means model. So our data has an overall group effect with some random error. And so if this is, say, I treatments, that's this setting. So if we have I different types of barley, or we have one barley with I different types of fertilizer, and we want to compare the mean yield, this would be a good setting. So the error terms are independent. They're normally distributed with some common variance. The terms, I is the number of groups. Sample sizes are different within each group. We have group means, grand means, the random error component, and the mu-i's are the true group means, which we often don't know. And we're going to let the individual sample sizes all total to a capital N. And here's the standard test statistic. This is the mean square error for treatment effect. And this is the mean squared, mean sum of squares for error, mean sum of squares for treatment. And we are calculating, hey, are the means equal or are at least too different? Under the null hypothesis, our test statistic follows a central F distribution with I minus 1 degrees of freedom and N minus I denominator degrees of freedom. When F1 is true, then the test statistic follows a non-central F distribution with the same degrees of freedom and the non-centrality parameter this. And so plugging this into R is very straightforward when you're calculating power, which will illustrate that. But calculating sample size, we need to introduce a little structure, because how do you increase N? Do you make all the sample sizes equal and increase them by 1 each time? Well, that's the equal samples case, or the balanced one-way ANOVA, and there's another video on that, and R has a built-in function for that. Here we're going to assume that the N's are different. So one approach would be to let the sample size in group 1 be K times N. Sample size in group 2 is K2 times N. Sample size in the ith group is Ki times N. And then you increase this variable here, 1, 2, 3, 4, 5. And what that does is it lets you to set up, allows us to set up any ratio we want. So assume we want a 1 to 2 to 2 ratio. Then when we increase our sample size, then we maintain the ratio we want. Or it could be 1 to 2 to 3 ratio, and then we increase 1, 2, 3, and then we just calculate power at each case, and then we stop when we've achieved the power we want, and then we've also maintained the sample size ratios that we wanted to. Okay, we're in R, and I'm on an Ubuntu Linux machine, and we're going to look at the unbalanced one-way analysis of variance. That means that there's unequal N's per group, but the goal is still the same. We want to compare the treatment means with an alternative at least 2 are different. Now to illustrate this, let's pick some values. Alpha 0.05, let's say 3 groups, sample sizes in each group are 22, 15, and 27. So this here is, we're going to illustrate this in a 5-group setting, so I commented it out for now. Let's create some data, and this is the F distribution under the null. So we need a rejection region here. So this is the rejection region. This is 0.05, and when we calculate a test statistic, if it falls in here, we reject the null hypothesis, saying that at least two of our treatment means are different. If it falls in here, this area, then we're going to say there's not enough evidence to reject the null hypothesis. So now on to calculating power and sample size. Now when we're under the alternative, then the treatment means are not equal, so we have to pick some values that make it true, the alternative true. And so I picked 120, 130, and 135. In our true variance, we'll put it 500. So there's GM stands for group means, and then our lambda ends up being this. So it's the sum of the NIs times each treatment means minus the grand mean squared. So the alternative distribution looks like this. So this is an F distribution, same degrees of freedom. And let's calculate the area for power. So we're trying to find this area, and to calculate area under a curve in an F distribution, we use the PF function, which is the cumulative distribution function. We want to go from the critical value with this numerator degrees of freedom, this denominator degrees of freedom, and lambda. So in this setting, we have 52.3% power. Okay, so if we want to have more power than that, this is one approach to do that. So we let the N1 be K, some constant times N2 some constant times N, and we set it up like this. So here we're going to have a 1 to 2 to 2 randomization ratio, and you can see that. So this is 1 times the NT, 2 times NT, 3 times NT. NT is it's the N that's going to be increased by 1 each time, and I think of the T as like a tick. Is this enough power? If not, tick, it goes to the next iteration. And so 3 groups, we're here, and we start out with sample sizes of 5, 10, and 10. We look at the power, it's 17%, it's not enough. So now we need to increase the counter to 6, but to do that will take a little while. So let's write a little while loop that says while the power is less than 80%, increase it by 1, check it, keep going until it's more than 80%. So we do that, and the sample size is needed to have 80% power and maintain our 1 to 2 to 2 ratio is 31, 62, and 62. We have 81% power. Now let's quickly do this with in a 5 group setting. So here we're going to let our sample size be this 33, 33, 25, 40, and 22. 5 groups. Let's calculate the distribution of the test statistic under the null. That's an F distribution. The rejection region is here. To pick values in the alternative, I am using this one. So we're going to pick true group means of 20, 30, 34, 22, and 28. Then we'll calculate the non-centrality parameter. That's our F distribution, and the power region would be the shaded green there, and to calculate power we'd get 60%. So now let's calculate sample size needed to achieve 80% power in this setting. So here we're going to let the K's be 1, 2, 2, 2, 3. Why? Just illustrative purposes. You can really make them anything you want. So this is going to be a 1 to 2 to 2 to 2 to 3 randomization ratio. So we'll do that. There's our first N. There's the lambda, and we calculate power, and it's less than 80%. So then we're going to put it in this while loop and increase 1 each time until we get at least 80% power. And we do, and we stop when we're at 28, 56, 56, 56, 84. And this maintains the 1 to 2 to 2 to 2 to 3 randomization ratio. So anyway, that's all I have for today. Hope you enjoyed it.